just put it in your pocket. The green light, I flip the switch to now.
Okay, yeah, thank you.
We got ready to go.
So all can
So
be...
I'll mention these two things,
Okay.
and then you can feel free to erase them both, okay?
Okay, yeah, great.
Okay, so let's get started with our next lecture. So just two quick announcements. One is that the public lecture is tonight. Juan Maldacena is delivering a public lecture. It's downstairs in G1B30. This is G130. That's G1B30. Just on the ground floor, it's one of the big lecture halls, the one closer to the parking lot. That'll be at 7:30 tonight. And then the other announcement was that if you want to go on the hike and you're not on Facebook, email Jasmine, jtbrewer@mit.edu for this weekend's hike. So we're happy to have Miranda Cheng, who's going to tell us a new set of two lectures, right?
Yeah, that's
about
right.
moonshine. So take it away, Miranda.
Okay, so yeah, two lectures on moonshine. First thing I would like to say is that it's a real pleasure to be lecturing here in the TASI school. I heard that you guys are the future of high energy theoretical physics. So that's certainly an honor. Second, yeah, it's on moonshine. So I assume that not many of you, maybe zero, is working on moonshine. So I'll try to, give a fun introduction on what it's more or less about. But please feel free to interrupt me anytime. And I reserve the right to say, no, let's talk about this later, right? So you don't have to worry about worry too much about asking questions. Okay? And so, well, I'll first start with part one. And guess what? The part one is going to be an introduction. And we will start with the question, what is moonshine? If you're thinking about booze, then it's in the right direction. And so I'll give two answers. The first answer is for non-experts. So which will be an answer that sounds good, okay, hopefully. So I would then say that moonshine refers to a certain connection between two types of mathematical structures that a priori have nothing to do with each other. So one of them is modular objects, which are certain type of objects I'll tell you about later. But in principle, they are functions that have nice infinite symmetries. Okay? And the second one is the structure of finite groups. Well, we all know what groups are. We all know what finite groups are. And one way that we usually encounter them is as symmetries of something, right? For instance, of an equilateral triangle or a square. These have finite group symmetries. And moonshine refers to some kind of connection between these two things. And the first part of the lecture, I'll show you a particular example of such an unexpected connection. And the second answer, well, I will give because before coming here, I was in Aspen in the Center for Physics for 2 weeks, and we have a program on moonshine, and we've been discussing this question extensively. And the consensus among experts seems to know that we don't know really what moonshine is. And I hope that in the second lecture, by the end of the day, I will convey this confusion to you, that you will get out more confused than you were, then you understand why it's kind of subtle to say what moonshine is. But this paradigm is what you should keep in mind for the lecture, and which is actually correct. But if you want to make this more concrete, then it is a little bit hard. Okay, so another question is, how about physics? There's not a single word of physics on the board yet, but I'm here hopefully for a reason, because there are certain physical elements in the story, actually a very important physical element. Because seeing this diagram as it is, you're just like, what the hell is going on? We don't understand. But what the success we have had so far in understanding moonshine comes with adding a third point in this diagram, which is some physical theory. Okay. And they deliver modular objects by computing, for instance, partition function or other physical quantities. And they deliver, is that too small? Okay. And they deliver finite groups as the symmetry of the physical theory. And once you establish the theory and the connection to the objects you want and the symmetry you want, so all of a sudden this diagram starts making sense, right? Okay, of course, if this is a symmetry of the theory and this is partition function or other correlators of the theory, then the two objects should be connected. So this is the way physics have been contributing in the study of moonshine. And in the broader scheme, the study of moonshine by string theorists fits nicely in the subfield in string theory that's called the string math, or physical mathematics, or you might have heard many words like this, which is, well, to use the intricate structure of string theory, for instance, the compactification. You can have all kinds of Calabi-Yaos and whatnot in your theory, and here you can gain insight about geometry and, for instance, representation theories of groups and algebras, and here through the connection to the special functions and the number theory. So sometimes the arrow goes this way. We're developing new math to gain a better understanding of string theory. Sometimes the arrow goes this way. We're using physics to solve mathematical problems. So then, after that, will be a little commercial time. Why we care about moonshine. So the reason to address this question on time in the beginning of the lecture is then you can make up your mind for yourself whether this is worth your time or not. If it's not convincing, you can ask me, and if I can't give you a convincing answer, then it's not worth your time, right? Well, as we said, first of all, it's a mathematical connection, and it's a connection between two things, and only in a few cases we have an understanding via physical theory in the above way. So most cases of moonshine is still completely mysterious, and it actually points to, you know, an unknown paradigm between the study of two subjects. And so you know, the dream is, maybe it's not true, maybe it will not be true, maybe it will, is that in the future, when you talk about, when you teach a class about one thing, you cannot skip mentioning the other, because there are so many examples of moonshine coming up. So we got to understand it and write that textbook, right? Eventually, someone. And why are there so many physicists? Well, not so many, but many physicists interested in studying such a connection. Well, first reason, still connections, but now connecting to, for instance, in this diagram, the connection between string theory and geometry is has been very successful and very extensive. But the connection to number theory is kind of weak. But many people believe that there should be a stronger and stronger connection there. And this is through the connection to modular objects. It's a great opportunity to connect to that part of mathematics. And second, inspired by the goal to explain moonshine, people have been having lots of fun searching and studying physical systems, or in particular string theory compactifications with large symmetries. Okay? So why do we care about it? Well, first, because they're beautiful, they have very distinct properties, but second, you might think, like, except for, besides using supersymmetry and so on, a system with large finite group symmetries will also give you new handles on physics, so you can compute more things than other systems. That's one of the motivation. And another motivation, which is kind of harder to explain right now, but many people believe that by studying this paradigm, we'll gain a better understanding of the structure of quantum states, as at least those that are protected by supersymmetry. So this I will have to explain once I get to tell you the concrete story of individual moonshine phenomenon. And the third motivation is probably that there's a lot going on. So it's a good time to start looking at this topic. Well, first, the first type of development is the discovery of new moonshine. So there seems to be more and more and more examples being uncovered of such different finite groups connecting to different modular objects. And these examples we typically don't understand yet. And once it's discovered, we are desperately looking for the third corner, namely the relevant physical origin of moonshine. And then inspired by this and this, people are also making progress in understanding the symmetry of typically K3-ish, if you know what a K3 is already. So I would say that it's an active field on the interface between string theory and mathematics. So that's the commercial time. Yeah. Well, where should I start? You know what a K3 surface is, right? So you can compactify string theory on it. But one thing you can do is that you can compactify it on K3 times T times S1, K3 times T2, K3 times another circle at T3, and you go on like this. Another thing you can do is to look at, orbifolds, quotients of K3, and then you get to some special Calabi-Yau, or if you're even more bold, and you can look at heterotic strings on K3, or K3 fiber Calabi-Yau 3 folds or 4 folds, and so on. Yeah. So actually, K3 will not appear anymore till besides the commercial till later. But a brief reminder, one-liner is that K3 is the unique Calabi-Yau 2 folds that is not trivial. Okay, trivial by trivial means it's just products of circle, namely a torus. Okay, and torus is too simple, and Calabi-Yau 3 folds is very hard. So K3 is like nice laboratory for doing things. Okay, so then we go to the outline. So the first part of the lecture would be about the physics. I cannot spell physics and math of monstrous moonshine. So the name is getting more and more exciting. But this case of moonshine is the one that's best understood, and it's discovered in '79. So that was ancient, right, before you guys were born, and then people have been working on it until, and in the early '90s, the main conjecture has been proven. Someone got the Fields Medal for it. Everybody's happy, and then the field sort of feels accomplished until 2010. There's a bunch of new examples till now, so people are confused again. Oh, after all, we don't understand moonshine. But this case, people, well, we don't understand everything yet, but we understand the idea. So I would like to use this case to illustrate what the main idea is of moonshine and going through some background. Okay? And after that, the second part, well, I already said this first part is intro, so let me add one more line. So the third part, I will tell you what's been going on with new moonshine, so it's going to be much more schematic, but hopefully more up-to-date in that sense. Okay, so now, to tell you about this moonshine, I will have to explain these objects a little bit, these boxes. So what is a finite group? Well, we all know what group is, right? If you have elements A and B, and A times B has to be in it, and there's an inverse, and we know what finite means, namely the group has finitely many elements, and finite groups can be decomposed, quote unquote, into simple finite groups. It means that you can take simple finite groups and compose them into a finite group, a general finite group. So they're sort of like the primes in a number. And so, of course, there are infinitely many simple finite groups. Well, but the surprising thing is actually that people have actually classified them. So there are 3 infinite families. For instance, to see that there is infinitely many finite groups, for instance, every cyclic group of prime order is a simple finite group. It cannot be decomposed further, so that's one of the families. And then there are 26 or 27, depending a little bit on your definition. that don't fit in the infinite families, so they're called sporadics. I think the name explains itself. So to explain what's so monstrous about the moonshine, because, well, there's a largest one of the sporadics. It's called monster group. And then the common notation is this script M. And what's so monstrous about it? Because the number of its elements is more or less the same as the number of atoms in the solar system. So it's a humongous group. Well, it's finite, okay? But it's huge. There are so many elements. But fortunately, the conjugacy classes is much smaller. There's only 194 of them. So that just means, like, if G and G prime are conjugate to each other, you don't count them twice. And the theorem for simple finite groups tells you that there's 194 irreducible representations, namely the representations that cannot be reduced further. So we all know what representation is, but to set up the notation, let's just say that the representation is a pair. Usually we only talk about the vector space as the representation, but in fact we need a row that maps G to, let's say, GLV, right? So then what the group character then is defined as, we usually write it like this, but what it really means is that we're taking the trace of this matrix. Okay? So if you want to know about a finite group, one thing you really want to see is the character table listing all the group characters for all the irreducible representations. And because there are as many conjugacy classes, and this is, of course, a class invariance. If G and G prime are conjugate, the character will be the same. And because these two numbers are the same, so you get a square matrix that you can invert. Okay? So for the monster group, there's 194 of them. And I won't give you the 194 times 194 matrix on the board. But let me just give you a few entries. Okay? E is the identity matrix, right? So this will tells you that the E character, the identity character, is just the dimension of the vector space. Okay? And the first one, if we order 194, it wraps by their sizes. Then the first one is, of course, the trivial representation. And the second one, so this also shows the difficulty to study the monster group. Not just the size of the group is huge, the smallest non-trivial representation is also huge. It's kind of hard to write down 196883 times 196883 matrices, which are what this is about, right? What these are. So it's really hard to study this group a priori. Okay, and finally, well, I'm really not going to write down the number. It's just humongous, but there are 4 of them. Okay, so these are sporadics. Yeah.
So, just a question for the situation.
Mm-hmm.
Is there something? It seems like the nice simple finite group. You're going to tell me some sporadics including the monster group.
that's what I was going to write after Q. Great. Yeah, you're welcome to read the proof. It's about 2,000 pages. I haven't read it. Yeah, but there is a proof. Yeah. It's actually not trivial, right, to claim that there's a proof of such a theorem, because, I mean, the proof was announced, and then it's like 1,000 pages, and then people actually read it and found loopholes in it, and then it took another 10 years, another few thousand pages. So it's a real, human endeavor to do this. Inhuman endeavor, yeah. So to ask the question, why do these sporadics appear? What do they have anything to do with anything? Because, as we said, for dihedral group, we understand it as the symmetry of some shapes. And what plays the role of these shapes for the sporadics? Well, the answer, unfortunately, is still we don't really know completely. But I can, again, try to give you some partial answers. So for many cases, we know that there are special lattices and so on, and error-correcting codes, which are closely related, that play the role of these very symmetric shapes for dihedral groups for the sporadics. In what sense? Well, one big class of the sporadics, so 26 I can get about, well, I don't know exactly what number, but somewhere like 10 from these very nice lattices called Niemeyer lattice. Okay, so the theorem says that there are precisely 24 even self-dual. Well, as string theorists, we're familiar with even self-dual lattices. They're very good for us in defining modular invariant partition function and positive definite. So the signature is positive definite lattices in 24 dimensions. So there are two 24s on the board that has nothing to do with each other. So one of them is what's called the Leech lattice. And another 23 of them, I'll use the notation nx, where x are some kind of combinations of ADE or root systems. So a root system of the lattice, meaning like the length square 2 lattice. So which is, of course, the smallest that's allowed in the even lattice. Okay, and Leech is singled out because there's no such small length vectors. They don't exist. Okay, and what do they have to do with sporadic groups? So you can get 7 sporadics from taking subgroup of the symmetry group of the Leech lattice. And you can get a few more from here. For instance, let's define its automorphism lattice in this way, in the obvious way, but you mod out by the wire group of the root, because since they're length 2, then square 2, you can define a wire group. And then if x is the simplest one in the sense that it's just a bunch of A1s, then gx is what's called the M24. It's or Modular 24, which is, you know, the more friendly member of the sporadics. It's not as scary, monstrous as monster, but still very interesting. Okay, so now the question is, how about the monster, for instance? There's no lattice. There's no lattice with this symmetry. What's a natural representation of the monster? And the cool thing about monstrous moonshine is what people say about it, which of course makes some sense, is that the most natural representation with a given certain definition for natural is infinite dimensional and is what shows up in monstrous moonshine, as we will see later. Now I sort of have explained the first object. I'll try to explain the second object. What are the modular objects? In particular, we'll focus on something that's called modular forms. So what are they? Well, first of all, these are functions on the upper half plane. And we know that upper half plane has a natural symmetry given by Sl2R mapping a point to another point in this way. And Sl2Z is then the discrete subgroup of Sl2R, where ABCD has to be integers. So that's one picture, the first picture that's relevant for modular forms. Another picture that's also nice to keep in mind is that Sl2Z is, of course, what stabilizes a two-dimensional lattice. Right? When you do the ABCD, what you're doing is changing the basis of the lattice. Right? For instance, if you write the lattice like this, it's still the same lattice, or the points are the same. And another nice picture to have is that Sl2Z is a mapping class group of torus. Well, one way to see that is just if you identify the sides and fill in this space, it becomes a torus. And for instance, it corresponds to how you slice a bagel. Well, usually people slice it like this. But of course, you can also slice it like this. You just bite in it, right? I don't want jam, I don't want butter, I just want to bite in my bagel, and then it becomes like this. So these are Sl2Z transformations. So modular forms are first of all, functions that transforms nicely under this group we like. For instance, should I start a new board? Yeah, why not? Yeah. Yeah, I was all of a sudden feeling German for some reason. Thank you. Well, I'll give you an example of a function that transforms nicely under this. And you just have to believe me. So I'll call it tau. I'll call it j. So we know that Sl2Z is generated by two moves. One is tau to tau plus 1. We call it the T transformation most of the time. And then the other is a negative reflection. Well, to be honest, it generates P SL2Z, but it's okay. It's a harmless lie. So this is our fundamental domain, right? All other points is mapped via these moves to a point in this box. So to check that this function is invariant under SL2Z, you just have to check that they're invariant under this. And there's actually a unique such function that goes like Q to the, where Q is e to the 2 pi I tau as you go to the cusp, infinity, right? Or, yeah, or low temperature limit, if that makes people happier. So how do you see that it's unique? Well, one way to see that it's unique is the following. Because this fundamental domain, if you compactify it and put in some points, is actually a Riemann sphere. So you just have to show that J function acts as a isomorphism between the two spheres. So this pole will come to become the point at infinity here is this. And then you need to specify 3 parameters, right? For every isomorphism. Then you specify, the location of the pole is here, and the coefficient, and the next term, it has to vanish, right? It starts with the positive powers of Q, and you're done with uniqueness. So how many more minutes do I have? 12. Okay, great. And another cool thing about this function, there are many cool things. The first thing is why it's so important is actually it's unique. And a consequence is that all SL2Z invariant functions are ratios of polynomials of this. So you can see this showing up, for instance, in your F-theory lectures, I believe. So that's really the canonical object. And another thing is that now let's write down this Fourier expansion. So, does this number look familiar? So it's almost the same as this number. So we can identify this coefficient 1 as the dimension of the trivial. So this is the dimension of the trivial and the first non-trivial guy. And this is actually so this equation, so the start of monstrous moonshine started with the so-called Mckay equation, which says 196AA4 equals 1 plus 196AA3. And people went on to do the game for other representations, and it was sensational because J function is such a canonical object in the study of modular forms or in number theory in general, and has a lot of applications in the study of geometry. And it turns out to have this weird relation with this oddball that's called the monster group that was, and imagine that at that time the monster group was conjectured to exist. It hasn't been proven to exist, but it has. But people also conjecture that if it exists, it have to have certain certain properties, and with that properties, people computed the first few numbers that shows up here, and all of a sudden, it was observed that it has something to do with this very canonical object, and that was sort of the hint of moonshine. It's unique if I specify this behavior at I infinity. Otherwise, as you said, every chiral CFD that's self-dual will have this partition function. And we'll have partition functions that are, what did I say, ratios or polynomials of this guy. So that's very powerful, this uniqueness, as we will give you an example later. Okay, so the usual way to present the story from now on is then I tell you what mathematicians did subsequently after this amazing observation and how do they prove it, and in the end what the relationship is to physics. But
The partition function for 24 free bosons, is it just some ratio that?
1 over delta?
Yeah.
Well, 1 over delta, no. Okay, so 1 over delta has a weight. Okay, what does that mean? What does that mean it has a weight? And I'll tell you why it's not modular invariant. Right, because, well, this is, as you can see from the uniqueness, modularity is very, very constraining. But you can get more interesting objects that you actually need in CFT if you allow the function not just to depend on the shape of the lattice, which is given by this tau parameter, but also the size of the lattice, right? So if you, so let's call this function f, and lambda is the lattice, and if you allowed it to rescale like the function to rescale like lambda to the power k, if you rescale the lattice, then you get the concept of modular forms with a non-trivial weight k, okay? And for instance, 1 over delta, the 24 bosons will then have a weight for the reason that you will see, and I will remind you in 3 minutes, if that's okay. Yeah.
So, how are these coefficients obtained, like the upper board, like, so I guess you're just matching, you find them out somehow and then they agree with it, is that correct?
Mm-hmm. So these coefficients are well known. Okay, this function people have known for a long time. I can actually give you, for instance, some closed form formula for it if you want, if I can get the, so let's go. To the power, what's the power? 24, I think. Yeah. And then minus 744. If you want to check on Mathematica, I think this will give you these numbers. Any more questions? 1 to infinity. Yeah. So this pattern breaks. So what is believed to be true, and right now we know it's true, that let's call this Cn due to the n. And then there And the conjecture, which is true in two ways, is that there exists monster representation such that the dimension of Vn is Cn, where C is defined by putting that in Mathematica, and this is some representation. But this is a stupid conjecture because, of course, it's true. Because we have one-dimensional irreducible representation. But don't worry, that's not what Monstrous Moonshine is about. There will be a meaningful conjecture, which is also true, fortunately. More question about this? Well, as I just said, it's not, because all right, so then you have to define what do you mean by taking out. But I promise you, there's a meaningful conjecture I'm going to write down, and the representation, if it exists, is unique. Okay? Anything else? Yeah. That's right. You can quite easily see that by sort of a refined version of Cardi formula. Okay? So, as I said, I'm going to introduce Monstrous Moonshine in a bit of different ways, because hopefully in a way that I'll now talk a little bit about physics, and hopefully after that you will all guess what the true story of Monstrous Moonshine is without me telling you. Because as I was advertising, once you know the physics, it's actually not as shocking as it appeared. And also through this way, hopefully you will see a bit more clearly what the current challenges are to understand the new cases of moonshine. So the third topic is going to be the CFT, especially the orbifold construction. And I'm lucky because Sheehan has taught a lot about 2D CFT already, so I can just, be very brief and just wave my hand and draw some pictures, and hopefully. So for our purpose, we want to know what modular invariance comes from and how it generalizes to different cases. So just a quick reminder. Well, let's think about the partition function, and imagine if we have left and right movers, okay? And in the canonical quantization, in the canonical picture, this is defined as a trace over your Hilbert space, right? And then you have like the left and right moving Hamiltonian, or in other words, you have like something that's given by phi tau 2 plus 2 pi I tau 1 plus the momentum right? And then I'm splitting the tau into the real and the imaginary part. And so you know all this very well. So just to remind you, the basic story, I actually use a more sort of geometric pictures, but the upshot will be applicable to non-geometric CFDs as well, but this is just for convenience. So since we have a 1 + 1 theory, and then so the Hilbert space is constructed by, for instance, by quantizing the space of mapping the one-dimensional space, which is a loop in this case, to some space M. Okay, so such a space of maps is called the loop space of M, and then if you quantize it, then you get the Hilbert space. Okay, that's in this scenario. It looks like this. So then you take the trace, and then you realize that you can rewrite this as Q to the L0 minus C over 24, and Q bar to the L0. Right? While Q is again defined as the exponential of tau. But you also have a picture of doing a path integral. So you identify these two sides, right? And then so you're mapping, your path integral is over, mapping a torus with a given complex structure, and then weighted by the action. Right, just because if you have a cylinder and you glue it, that becomes a torus. And here the modular invariance can be pictorially understood as the fact that SO2Z leaves a torus invariant. So you get the conclusion that this has to be the same when you do the two together. When you do this, mapping the tau and tau bar in this way. Okay, so that's easy. So just an example to answer someone's question about 1 over delta. Then for a free boson, well, let's just say that M1 is, well, let's say R. So you have a free boson theory. And then the Hilbert space is given by, of course, you have many oscillators, something of this form, and the zero modes momentum. So if you take the trace, now we can compute this. This is given by and this is modular invariant, right? So this part comes from, integrating over the zero modes, and this part comes from C over 24, and this part comes from the oscillator modes. Okay, so very simple example. So for our purpose, we want to do something a little bit different, a little bit more. We want to have a more refined version of modular invariance to connect to monstrous moonshine. And in order to do that, we already know that our problem has a finite group symmetry. So the question is what we can do when your theory has a finite group symmetry. Well, that brings me to the topic of, the twisted sectors of CFTs and orbifold. By the way, if you look at the monstrous Moonshine literature, people usually talk about vertex operator algebras, but since I'm teaching in TASI, I'll avoid using that language. But everything should be understandable in terms of CFT language. So for instance, they will call this the twisted module of your chiral algebra and so on. Okay, so what can you do? So let's again give you, take an example, a geometric orbifold example, just because that's easier to explain, but we don't have to be. So for instance, there I call my target space M, and imagine that M has a finite group symmetry. So the loop space, so the space you have before you quantize the theory, also will inherit the group action. And after quantization, you say that the group will also act on your Hilbert space. Moreover, if everything's all right, you'll see that the G action commutes with the Virasoro symmetry of the CFT. So it acts on each component, the eigenspace of the Hilbert space. So what you can do, apart from computing the partition function, you can compute this trace. Well, it's well defined, right? Because this commutes with what's here and what's here. So how about the modular invariance? Let's go back to that the derivation of modular invariance and see what changes. So now, if you want to, and this, I'll write it like this. So in this box notation, that's when both sides have identity. So why do I write this? Because if you want to write this as a path integral, you're summing over map into your target space that has a twisted boundary condition or a twined boundary condition, namely that this is still, oh, I kept writing 1 for identity, but this is still, is it better? So this is still periodic under this, when you go around the spatial circle, but no longer so when you go over the time circle. That's what inserting this guy in the trace means. So now you get a torus with decorations, right? So Sl2Z will no longer be the relevant thing to consider. For instance, if you do an S transformation, tau going to -1 over tau, it corresponds to taking this torus with this generator and making something different out of it, right? So this will be the new generator. So you're exchanging time and space circle, more or less. Right? So if you do an S transformation, you'll get G downstairs on the spatial circle and E identity on the time circle, temporal circle. Oh, is it that bad? Even you cannot see. This. Okay, help me to draw a cutoff, a wall. It's hopeless? Okay, then just keep coming. You can walk around here. It's okay. Right, so then if we consider the Sl2Z transformation, it's also natural to considering changing the boundary condition here. That has the interpretation of what's called the twisted sector. So to use again the geometric language to see what the twisted sector is, let's consider the geometric orbifold of this target space, right? So that means if 2 points x and x prime are related by a g action, you identify them. So then you're looking at, if you look at the loop space, you're looking at maps into the original target, but you allow for a twisted boundary condition. And so this decomposes into pieces like this. Which is defined in terms of the twisted boundary condition. So the interesting thing is, if you look at such a twisted boundary condition, it has a residual symmetry. Right? It's not a whole symmetry anymore, but the residual symmetry is given by the centralizer, what's called the centralizer of the group element. So this is defined as elements that commutes with H. Because you can check that if you act on phi with H, so namely for each point on the loop on the image of M, you act on it by G, because they commute, so they again belong to the same loop subspace. Okay? So hence you can compute not just the S transformation of this, which is the H twisted sector after quantizing this subspace. And then the same thing. And you can also consider H and G by inserting G here. Okay? So now I have a redundant equal sign, but that's not illegal. Hopefully you get the idea. So from the torus picture, we know how it transforms. It transforms like the following. I just erase this redundant thing and make it into something meaningful. G A B. I have to get my A B. Yeah. G. This is nothing but using the same argument with decorated torus, right? Because before you're looking at this, And now let's say you want to change your generator of the lattice or change the way you slice your bagel by choosing this as the basis, right? Then, of course, it carries a new boundary condition by going this and this. And it only makes sense, it's only meaningful because we have required a G and H commute. Well, another way to say this or to look at this, if you're more familiar with defects, is that you wrap around line operators separating the boundaries, separating the different phases with like G and H tagged in that. And the phase and the defect lines can cross only if you go around, you get identity. That's another picture you can use. But this is simple to draw. Well, so that's one thing that will be relevant for the monster story. And another thing, since I ran out of space, I jumped back. I apologize for people over there. Another thing you can do is you can come up with a new theory called the orbifold theory by putting different twisted sectors together. I'm already implicitly doing this, but now what you have to do is to take the sum into account, right? So you take the sum into account. And on top of that, what you need to do is to project out states that are not invariant on the G itself. So you get something like, so you sum over twisted sectors. So this sum and this sum is sum over what commutes with it for the reason that I said before. And you do this. And you do the sum that will give you the number of final states in the orbifold theory. Okay? This is a slight lie. The lie is not that severe. You might have phases here, depending on GH, sometimes called the discrete torsion. It's related to the fact, the following fact. It's not central, so if you want to take a break, it's a nice time. But the fact that what I draw here, right, is actually some representation of the group, right? Not the group as abstract group itself, right? There's some representation acting on the theory, acting on the space. And sometimes it happens that this representation is only projective representation. So rho of G times rho of H equals rho of G times H only up to a phase. And that phase is related to the things that can happen here. But I want to give you an example of the orbifold theory, which hopefully will give you a happy feeling of like being closer and closer to understanding monstrous moonshine. And then it will be a good time to stop, I think. Right? Yeah.
We're supposed to have like 2 minutes left. We started a few minutes left.
Okay, we should wrap up. Yeah. So I'll be really quick because you can actually find this example in Xi's lecture notes. But I don't think he talked about it. I'm looking at him. So I'm going to do his job for him. So let's take a bunch of free bosons and now chiral bosons. So we forget about red movers. Sometimes you can get away with it, like in this case. And often this will make me very happy. And so 24 free bosons. Okay, but it's kind of boring. So let's consider a non-compact target space. So we mod out by our favorite Leech lattice. So this is a specific 24-dimensional torus, the Leech torus if you want. And then we consider a symmetry that's as easy as it could be, which is generated by an order 2, of course, an order 2 element. That's just reflecting all the 24 bosons. And let's look at the partition function of the original theory, forgetting about G. And we know that when you have a torus like this, you get your usual oscillator part. In this case, 24. So here you get your favorite delta. But you also get the contribution from the winding and so on. So you get the theta function of the Leech lattice. So if theta function of lattice is you sum over lattice points, and you take the norm squared and you divide by 2. So first, it is a partition function of a CFT, so it's Sl2Z invariant. And this theta function, of course, doesn't have poles at I infinity. So it starts with q to the minus 1. So then we're almost at a J function because of uniqueness. But there's a constant term, a constant piece, as opposed to the J function. And we know what the constant piece is because there's no norm square term here, right? Because of its Leech, no roots. So there's no constant piece coming off that, so it's just the constant piece that comes from here. So this is J plus 24. Now you see how powerful the uniqueness can be used in real-life computation. And to apply that formula, we have to sum over 3 other pieces. So the full story, the full partition function, let me call that the Flm partition function, which I will explain later, is given by 1 over the size of G, so 1 over 2, and okay, this we have computed. And this, well, we have a minus boundary condition on the spatial circle. So that will kill all the lattice part and put a plus sign here. Sorry. Right? And because if you have odd number of oscillators, you get a minus sign. And here, you get, in the twisted sector, you get antiperiodic bosons. So that's like fermions. So you get the 0 modes, and this works other way here. And the modes grading is a bit different. So you have 24 of them. Am I screwing up something? Yes, I think so. 2 square, that's how fermionic zero mode works. So you pair them up. And if you have this, you get the same thing, but with this plus sign. But there's a choice you can make on how G acts on the ground state. So you make a choice such that this is plus, and the rest is the same. Okay? I think this is right. So you, again, you split it into 2 parts. Yeah. And then if you put everything together, the net effect is just that you kill the 24 and you get a J function. So this is a relatively simple CFT that was constructed by Franco, Lesbowski, and Merman in the mid-80s after Monstrous Moonshine, because people are looking for systems, algebras, or whatever that's that relates to the J function in a natural way. And this is the Cairo CFT, or Cairo algebra, that they came up with. So that'll be the end of my first lecture. Yeah, that's the name for 3 gentlemen. Edward Franco. Huh? There are 2 Francos, and did I say Edward? Oh my God, no. They're really different, except for, well, Edward also, and they both have done a lot of work on vertex operator algebra to make things worse. So this is Igor Franco. Yeah, sorry. Okay, so I think it's about, the book is about 84. I might be a few years off. Don't kill me on that. So that's what FLM stands for. So huh? It's not really.
Well, Lagrangian, there is not really an action on Lagrangian integration. Then how do you make sure that the calculation must be modular power?
Okay, yeah. First, it's a historical remark. So they developed the Cairo CFT in the language of vertex operator algebra independently of physicists. Well, not just they. Before them, there was Borchert and other people, and Cutts also played an important role. So indeed, their consideration, their language was pretty different from physics language, and certainly there's no Lagrangian showing up. And second, you're saying that, oh, how do I see this torus computation? Indeed, so strictly speaking, it's not. That's why mathematicians needed an independent proof of modular invariance. So the status is, well, I'm not going into the detail. We can talk about that later, but after FLM, there's Igor's student was Drew. Drew had the theorem proving the modular invariance for this theory, and of course for many other classes of theory. So classes in our language are with classes of Cairo CFTs satisfying certain conditions. Yeah. But I mean, not just orbifold, right? Any VOA in general will have the. Mm-hmm.
What the total number of physics
Two. I mean, identity and for a general group, that's the number of conjugates classes or number of group elements, depending on a little bit on how. Of course, but then they're equivalent. You get equivalent copies. Yeah.
That's the series expansion of the tau.
Sorry. I want to tell you that what I said was also a lie. If you have projective representations and so on, then you can get spaces and so on. But yeah, but and then you have to be careful with the face in front of it. But eventually it all works out. Back to your question, no, it is an infinite series.
So the dimension
So
pattern doesn't.
Indeed, it will stop being 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4. No, that's not the general pattern. The one thing that's really significant is that there exists a representation.
So if we did one of the other dematerializes, the only thing that would change would be this theta function of tau.
Yeah, your change of constant.
It would change the constant piece.
Yeah.
So then.
But you can still do the same thing, and often you get something interesting.
Okay. So then the only reason we need to leave lattice in particular so that the 24 is canceled.
Well, yeah, and if the hindsight, the punchline is this conformal field theory has monster symmetry. If you start with other things, you won't have. Well, yeah. You mean like it's dual to C equals 24 3D gravity? Yeah. So there are statements like this, but well, we can talk about details later. But the first thing you have to keep in mind is that C over 24 equals 1 is really not weakly coupled gravity or anything resembling that, because it's extremely quantum. So how much of the gravity intuition you can use? Well, you can say many things about it, but I mean, I think that's one thing clearly that we should be careful with. I don't know if she has better comments on that. Yeah.